Okay, so today we'll continue with economic dispatch, basically solving this type of optimization problems by adding inequality constraints, right? So far we've been looking at this type of equality constraint. After this, we'll look at what happens when you have inequality constraints, which is sort of more complicated for the way we're solving it. But let's do a review for the equality constraints. So for equality constraint, again, there's a simple procedure, right? So you write the equality constraint like this, you put it in, you take derivatives, and at the end of the day, basically what you conclude is that the optimum, the marginal costs are equal. So that's what you get this type of linear system equations, and then you can just solve this linear system equation, right? So there's a sort of clear interpretation for this thing. And the physical interpretation basically is the same, right? It says you have some load, and then you look at the price. If basically what happens is if you're generating too much, right? So this thing, if this thing is negative, that means you're generating too much. You reduce your cost. You can get a less costly solution. And then that goes down. If you're not generating enough, the increase your price will go up because you need more generation. So for this sort of one equality constraint, then the interpretation is quite simple. It's very straightforward interpretation to this. And then basically all it's saying is it has to be equal because if it's not, then you would choose another generator, right? So the marginal cost has to be equal. So there's another interpretation to this, which is you can think of a sort of more differential interpretation. So you can set up, so you can, if we're given the optimization problem, let's say minimize some cost. Okay. So we can do is you can write something called a Lagrangian. So Lagrangian describes, so this is script L for Lagrangian. This is a function of three variables, your x1, x2, and the price lambda. And we have a C1 plus C2 plus lambda L minus x1 minus x2. Okay. Right, so that you can write down this Lagrangian. What you can do is you can take derivatives and solve the resulting equation. The interesting is what you can also have interpretation as you can ask the following question. If you look at this optimization problem, what is it actually a function of? Okay, so another way to think about the optimization problem is to think it as a function from the load to the optimal value. So you can think of this as a following function. Okay, so this is often a useful way to think about optimization problem. It says, you give me a load, give me some load. I can go and solve this optimization problem. There's a value. You can look this function not at, sorry, so instead of looking at getting the optimal solution out here, look at this as a function. Okay, so this is the interpretation you can have. Now for this function, you can ask the following question. What is the derivative of g respect to L? Because let's say you're operating the system. A question you may have is if I change L, how does my cost change? So that's another question, sort of very natural question you can ask. If I change my total load, how does the value, how does the optimal cost change respect to total load? So if you look at this function, what is this value? So if I increase the load by a little bit, how much does the cost go up? By lambda, right? So this goes by lambda. But when you take the derivative, you look at this equation. What is the derivative with respect to L? This is the lambda. Lambda is the derivative with respect to L. So this is lambda star. Okay? So this is the optimal price you get by solving this problem. So another way to interpret this Lagrange multiplier is this is actually the derivative of the cost with respect to the load, with respect to the constant amount you have here. Okay? So this is actually a very useful way to think about the problem. Basically, you can think this as a function. Then this tell you what the derivative of the function is. Okay, so this is quite a useful way of thinking about the problem. Okay. So if you have multiple constraints, for example, you can think of each of the multipliers as a partial derivative of this function. It tells you if the function parameter changes, how does the problem change? So this, of course, makes sense because the rest of lambda star, this is the dollar, let's say, per megawatt. Right, so this is the price of electricity. Right, so this is the price. So if you change the load, then of course, generating more load give you this price. Okay. So this relates to the sort of the physical parameter L to a cost. This relates physical L to a cost. Okay. Any questions about this? Okay. So this is another way of where sort of this is. You can think again. This calls for duality. This is called a dual variable, where a dual variable becomes very useful to you. So the theory for duality is actually sort of very, very rich. It's a quite rich theory of duality. Basically, it's a question of this type. When you want to view the optimization problem as a whole, as an object, normally the property of the object is actually given by these sort of multipliers. Okay, so quite a bit of theory behind this. But for us, when you're solving your problems, any of this interpretation works. So they are basically give you the same result. So if you have sort of multiple inequalities, it still works the same way, right? You can have 0, so you have m of this equality constraint. And then what you get is you associate a variable to each of these things. Right? So instead of having one multiplier for each of them, you give them a multiplier. So your Lagrangian now becomes f plus lambda 1, omega 1 plus lambda 2, omega 2, and the m. Okay? And you solve the problem exactly the way you have solved it before. So when you solve the problem, what you get is you get the following. You have x1 plus lambda 1 xn plus lambda xn plus 0 together with so together you have n plus m equations, n plus m variables. Okay, so same number of equations and variables, and again you can solve the system equation. So the homework we have now, it's the new homework. The first question asks you to solve this problem. Right? You're given an optimization problem with two constraints, with two inequality constraints, with two equality constraints, and you have two multipliers. You get a bigger system equation, and that question asks you to sort of have some physical interpretation of what's going on with this question. Is clear? Any question with equality constraint? In this class, the equality constraint is actually fairly easy because all the equality constraints we have are linear equality constraints. So not much can go wrong here. Yeah. Right. Yes, it's a local interpretation. So it's a derivative at that point. For the slope at that point. Any other questions? Okay. So if it's non-linear, then that's a harder problem to solve. We're not going to look at very much what happens when the equality constraints are non-linear. So your homework asks you to explore how a computer may go about solving this type of problems, but that's probably the only case we'll see it. Okay. So this class, what we'll get to is we'll look at how to solve the problem when we have inequality constraint. Okay, so inequality constraint means instead of this equal to 0, what we'll have is something less than equal to 0. So of course, you can write this sign however you want, okay? So you can write this as greater than equal to or less than equal to, it doesn't matter. But convention is if you're minimizing something, the convention of the inequality constraint is always less than equal to 0. And that's just by convention. Okay? So if you look at this type problem, for inequality constraints, it's always less than equal to 0. Okay, we don't have inequality constraint that's exactly less than 0. Okay. So we don't solve problems where this thing is a strict less than. Anybody know why? We don't solve this something that's strict less than. It's actually a subtle but important point, as you cannot replace this with a strict inequality. Almost all the inequality you will see is this will less than equal to. We're never good. We cannot solve problem typically if you have strictly less than. Okay, so the reason is your computer can't distinguish very small numbers from 0. That's actually how you solve. Okay, so if you have strictly less than 0, your computer actually cannot tell whether that is true or something very close to 0. Like the computer, there's no notion of exact 0 inside your computer. Okay, so when we solve problems, we typically need it less than or equal to. Okay, so equal to 0 is always a choice for this type of problem. This actually, there's sort of deep reason behind this has go to with sort of computational complexity. Why this cannot be strictly less than, but just something to remember. You cannot ask the computer to give you a strictly less than solution. Okay, so you can have something exactly equal to 0, and you can have things less than equal to 0. Okay. So the example is, of course, dispatch, right? So here what we can have is x1, x2 normally has to lie within some limits. Lie within a maximum, they have to lie within a minimum. So they have to satisfy some bounds on the problem. Okay. So then if you want to solve this problem, you have both an equality constraint and an inequality constraint. So your problem goes to minimize some cost, subject to x1 plus x2 equal to L. And then now to use the mechanism we're teaching this class, you have to make all these things into that form. Okay, you have to write this type something less than equal to 0, something less than equal to 0. In this case, what you write is you write x1 minus x1 max, that's equal to 0. x1 mean minus x1, that's equal to 0. Okay, so this is how you would write the inequality constraint. Any questions about this? Okay, so when you solve the problem, basically, we will teach you a recipe of how to go about solving this. The recipe works if everything is in this form. Okay, so whenever you got a problem, you have to convert things to this form. Then you turn the crank, and we'll give you a solution. Okay. All right. So, okay. So basically, we're trying to get to how to solve this. The idea is still you have Lagrangian multipliers, just a more complicated version of Lagrangian multipliers. The note is the way sort of I will present it in class is not how your computer will solve about it. It's not how we think about optimization problem these days. But to get to really how your computer will approach this, we'll take an entire other class just to get this point. So in this class, I'll teach you sort of a dumb algorithm. That's not how the problem actually solved. It's a dumb algorithm because that's the only thing we can cover in like a week. Okay, so what you see is a fairly dumb algorithm. What you should get is the sort of the idea, intuition behind the algorithm and behind the procedure. Right, so if some of you are very familiar with optimization and you want to call a solver to solve this, sure. Right. So there's nothing preventing you from doing that. But if you don't know for how convex optimization or linear programming works, then just follow the recipe that we'll see in this class. It's sufficient for the problem you see in this class. Keep in mind, really, that's not how for practical algorithms work. Right? It's really not how things work in practice. But the algorithm we'll cover that will give you intuition of what will happen. Okay, so if you think about this kind of problems, right? So what does a feasible set look like? Right? So if you have this kind of constraint, on x2, you want to draw what are the possible right? So what is the possible sort of set of solutions? Basically, the linear constraint goes something like this, right? You must lie on this line. This is x1 plus x equal to L. Then the rest is just described for a box. Right? In addition to living on this line, you have to live in this box. So your box looks something like this. Right? So this is your box. And then at the end of the day, where can your solutions lie? Your solution has to be okay, so where can your solutions be? Your solution has to be both on this line and inside this box. That's the whole idea of this, right? And the problem that arises is basically, remember last class we touched, if you just have this linear constraint, you're optimal whenever the normal of the line, right, is sort of parallel to the gradient. The issue here is that it may be at these points where your normal is parallel to the gradient, but it's outside the box. So the idea is, how do you think about, if this, so how do you modify the gradient condition? Okay, so remember for unconstrained problems, we have gradient equal to 0. For equality constraint problem, we have gradient is parallel to the normal of the line. Now you have another constraint, so how do you modify that condition? Right, you have this sort of condition that gets more and more complicated. Okay? Right, so what can happen is, right, so let's look at this again. As you have this kind of constraints, you draw a line, and turns out that at this point, what you have is your gradient is perpendicular to the line. But then, let's say your constraint actually looks like this. This is what your constraint looks like. So where is your optimal solution? If you look at this graph, basically optimal solution is somewhere here. Right? So you want to get to here, you can't. So you keep going, 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 and you hit this point. Okay? So this is your solution. Okay. Any questions about this? Right? So this is our intuition. Right? This is our intuition. So now we're trying to formalize this intuition. Okay. So for this type of problems, what you can observe is basically there's some interesting observations. The first one is actually the upper and lower bound will never be tight at the same time. Right? So for some, right? So we're saying at this point, basically the lower bound, you're hitting the lower bound. One thing sort of trivial to remember is not both upper and lower bound can be tight at the same time. And when you solve the problem, don't solve a case where both upper and lower bound are tight. And the second thing you can observe is whenever you have this sort of box constraint, is that for practical situations, is it very likely that you hit many constraints at the same time? Like for this problem, for this sort of thing in 2 dimensions, how many constraints can be tight at the same time in general? Right? Is it likely that 2 will be tight at the same time? Can you intersect this box at both lines? Right? You have to get very unlucky for 2 to be tight at the same time, right? You have to intersect this box exactly at this point for both constraints to be active. Otherwise, only one constraint will ever be active, right? No matter how this sort of straight line crosses this box. So the thing to remember for this kind of inequality constraints is most times only a few inequality constraints will be active. Okay, most of the times is either as none of them are active or a few are active. Okay, so thing to recall is for only a few the active means right you're binding on an inequality constraint. So even in very sort of high dimensional problems, it's not very likely that a lot of the constraints will be binding. I think most problems that only a few constraints are binding. This intuition generalizes to actually very large networks. So you think about, let's say, the California system. Let's say you look at the California unified system operator, has about 20,000 lines or so. How many lines typically are binding for this even very large system operator? Any ideas? Let's say you have 20,000 lines, right? So sometimes you run into this sort of you're binding at the transmission limit. It turns out even for the very, very large systems, only about 3 or 4 inequality constraints tend to be active at each time. So this is very rare. It's very hard to intersect this as many constraints at the same time. Okay, so not too many constraint binding, and that's why the sort of mechanism we look at in class, you have some reasonable chance of success. We'll basically teach you a combinatorial algorithm where you trial and error which constraints are binding. That's the idea of the algorithm. And you want to solve this problem, you try this one binding, this one binding, this one binding, this one binding, and the combination and all that. So that's a trial and error algorithm. Okay, so thing to remember is, so binding constraints is important. This is called a, for binding constraints, is a constraint that's satisfied exactly. That's the idea. Basically, it says, I have inequality constraint. Let's look at this. For example, let's say I have max. Then this is binding or active x1 exactly equal to x1 max. Right? So this is, if this happens, it's called a binding constraint. If this doesn't happen, we can ignore the constraint. It's as if the constraint doesn't exist for us. Okay, that's the idea. So so most constraints, most inequality constraints are not binding. The 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 problem is that you don't know which one is binding. Okay, so the problem is that okay, so we know that most of them will not be active or binding, but we don't know, before solving the problem, we don't know which ones are binding. Okay, so the idea is you basically go and guess. You turn inequality constraints into equality constraints. You do that, you get a problem with equality constraints, right? You get an optimization problem with only equality constraints. Use the method we had to solve that problem. Okay, so that's the idea we're covering in this class. Okay, so is the intuition clear for this type of problem? The procedure will get quite bored. This is basically the idea. The procedure is just combinatorially try all of them. Right? So this is the idea. Right? So you're really hoping that most are not binding, the few that are binding, try to guess which ones are binding. Okay. So we'll do the same trick as before. Okay, so we'll also write down Lagrangian function. Right, we have this kind of optimization problems. So we introduced another new Lagrangian multipliers called mu. Okay, so lambda are the ones associated with the equality constraint. Mu's are the ones associated with the inequality constraint. Okay, so this has lambda, this has mu. You basically write out this form. Again, remembering you have to have this as less or equal to 0. Okay, this only works if your inequality constraint is something less or equal to 0. This is sort of required for the thing to work. Okay, so the procedure as you set this thing up, what you do is now you start taking derivatives. And hopefully you get an optimality condition as before, right? So without this, we're able to get optimality condition. So now we have this new terms. Let's start taking derivative again, and hopefully we get some other optimality condition out there. Okay, so that's the sort of entire trick of optimization. The trick of optimization is you need to be able to tell when I give you a solution whether this solution is optimal or not. That's the entire essence of optimization. Is can you tell whether a solution is optimal? Here we're going to try to get a set of conditions where you can tell whether a solution is optimal. Okay, so let's and this is done by let's start taking derivatives. Okay? So we're going to start taking derivatives. So our Lagrangian is so this function above. So let's take a derivative respect to x. So let's take a derivative of this L respect to x1 or xi. Okay, so we have so take a derivative. Okay, so one condition is that still the first order condition, same as before. It's when I take a derivative, what I need is I need this first order. So when I take a derivative, I need a derivative respect to x to be equal to 0. Okay, so this is what I need. This is one condition I need to be true. Right? Whenever I take a derivative with x, this needs to be 0. Okay? The second condition I need is with respect to lambda, this just give me I, this needs to 0. So this has the derivative with respect to x has to be 0. The equality constraints has to hold all the time, right? So I take lambda, equality constraint has to hold all the time. Now the tricky thing becomes what happens when I take a derivative of mu? Okay, so now the tricky thing is what happens when I take what happens for mu? Okay. So the thing this is tricky is because you don't know what this value is. Okay? You don't know whether this constraint is tight or not. So there's two things that can happen here. And the optimality condition with respect to this term now will look a little bit weird. This is called a, so what this will happen is you have the inequality, this must hold all the time. And what we have is you have mu I times gi equal to 0, mu I greater equal to 0. So this is the weirdness of the inequality constraint. As instead of everything being very simple, just some function equal to 0, now you have this kind of product term that comes up. And this is called something called complementary slackness. So it's just a fancy word. It's just a fancy word for what has to happen. So basically, what this trying to describe is the following. This product, I want this product to be 0. Why does the product have to be 0? Well, so there's two possibilities. Either the constraint is satisfied exactly, either your constraint is satisfied exactly at 0, or the constraint doesn't matter, or mu has to be 0. This is what the inequality is trying to say. There are two possibilities for inequality constraint. Either it's holding an equality, or you can completely ignore this constraint in fact exists in your file. Okay, so this is what complementary slackness is trying to say. Okay, so just to be clear, we get this point. This is not a easy, not a trivial point. To understand this as the following. So let's say we're solving the following problem. Okay? Let's say just one variable, single variable. Let's say x less than equal to x max, x less than equal to, okay, so let's say x in this range, right? And suppose I get, right, even let's be more concrete. Let's say I want to minimize f of x subject to this axis between 1 and 2. Okay. Let's say suppose you're solving this problem. Okay, some function you're trying to minimize and turns out x is bound between 1 and 2. Okay. Say x star is 1.5. Okay. Let's say x star is 1.5, right? Let's say you solve this problem, somehow you solved it, and you figure out x star is 1.5. Then for this problem, it's as if this two inequality constraint didn't exist for you. And the important thing is, if x star turns out to be 1.5, then whether you have this constraint or not, it doesn't matter, will not impact your solution. Okay, so that's the idea. If this happens, then the problem can be this of the constraint. Okay, so that's the idea of the complementary slackness. It's a way of describing, does it matter whether I have a constraint or not? An inequality constraint that's not binding, it's as if there is no inequality constraint. Okay, so that's the idea of this complementary slackness. Now, how do you tell these two are the same? You do this basically through few variables. You do basically through Lagrangian multipliers. So in this case, we can write as your Lagrangian as f of x plus mu, let's say 1 x minus 2 plus mu 2, 1 minus x, right? You have this Lagrangian. So this is your upper bound, this is your lower bound in this case. But in this type of solution, it doesn't matter whether I have this upper bound or lower bound. It doesn't impact the solution. Then what must the value of mu1, mu2 be? They must both be 0. Okay, they must both be 0. So here, mu1 equal to mu2 equal to 0 because the constraints are not binding. Okay, we don't know, the constraint doesn't bind, so it doesn't matter what if, right? So it doesn't matter if I have constraints. So you eliminate these constraints, you pick the coefficient to be 0. Yeah, so this thing should not exist. So let me just zero it out. Let me zero out by multiplying by 0. Okay. Is this clear? Is this at least intuitively makes sense? Right? So the actual proof of the complementary slack condition will take some work. That's actually not trivial to prove that's the automatic condition. So here I'm going to give a very hand-waving argument of why this is true. The actual proof requires actually a limit argument to actually do the proof. So here we're not going to do the limit argument. We're just going to sort of hand wave this way through. Okay, so let's say this is true. So now let's say you solve the problem, right? Let's say now you solve the problem. Let's say now suppose you solve the problem that x star turns out to be 2. Right? So let's say, for this problem, it's out to be 2. So here, the fact that you have a constraint now matters because you're hitting the upper bound in this problem. Now your constraint actually matters. So how do you describe that the fact this constraint will matter? As you say, well, let me put the Lagrangian, mu1 x minus 2 plus mu2, 1 minus x. So this one doesn't matter. This one doesn't matter. So mu2 has to equal to 0. This one does matter, right? I need the fact that I have the upper bound. I need to reflect the fact that my upper bound is binding. So here I need mu1 not 0. Okay, so that's basically the idea of complementary slackness. That's a way to encode which of your constraints will be binding through this process. Okay, so mu will not be 0 if your constraint matters, if your constraint is binding. Mu will be 0 if your constraint doesn't matter, that's not binding. Okay, so this is the encoding of the constraints we'll do. Okay. Any questions for this? The hand-waving argument of why where mu comes in. Okay, so you'll be seeing quite a bit. If you look at this week's homework, the last question is you have to run through all this first scenario. But the idea is still, you want to test which one of these constraints are binding. Okay. Yeah. It could be both be zero, right? So in the last case, they're both. Oh, you're saying why can't this be zero and this be zero? It doesn't happen. There's sort of this only they're only both zero for a set of measure zero. That's argument. You have to get a very specific f for both to be zero. In general, it will not be zero. You have to sort of have a very specific corner with. And so in general, both will not be there. You can sort of get very unlucky with that. Okay, and in fact, that even when they're both zero, you can pick a positive mean. So in that case, what happens is your gradient will not be unique. You basically have a subgradient. And you can pick a subgradient where this is positive. So that's the argument. As you're hitting a corner, and there's many supporting hyperplanes. You can always pick one that says positive. That's sort of argument. Even in that case, you can find the mu that's not there. Okay, so but for this class, just remember if the constraint is binding, this is not zero. So to summarize this as complementary slackness is this has to happen. Okay, so this has to happen. There's two possibilities. One, this thing is zero, implying your constraint is satisfied, strictly satisfied. Your constraint is not binding, it's strictly satisfied. Or this thing is zero and this thing is positive. So I'll explain why this has to be positive later. But now just remember that one of them has to be there. Hence, complementary slackness means one of them, right? So one of them will be non-zero, or one of them will be zero. That's how you read the complementary slackness condition. Any questions for this? So really, if you want to know sort of the real detail about why this came out, so take the sort of convex optimization. Now go into much more depth about why these things are true. Right? So here we're going to give there's sort of geometric. So the really way to think about this sort of geometry, this sort of forms the right supporting hyperplane of the convex set. Now here we're going to give a sort of very handwave argument here. Okay, so this is basically it for the complementary slackness. As what you do is you write down this kind of condition, you guess which of the mu's are not zero, and then we do trial and error. Okay? So that's the idea. Okay? So solution using this is right. So through Lagrange multipliers, so we cover this page. So this is just writing out these conditions again, typing them out. And the thing to remember is that each inequality constraint is either binding or not binding. You don't know which one is a priori before you solve the problem. So solving the problem is basically trying to figure out. Okay, and the dumb way we're going to figure out in this class is we're going to do trial and error. Okay? This is our dumb strategy. As we're going to do trial and error to figure this out. Okay. Questions for this? Trial and error. Okay. So before we go through examples of trial and error, let me explain why sort of this positive constraint holds, right? Why when this is zero, this has to be positive. The reason you look at when this is positive, you look at the following. So this is positive because that's wording. Good. So again, you can look at the Lagrangian. Let's say this is fx plus mu of gx. Right. So why does mu have to be positive, right? So remember, you're trying to minimize this function, right? So you're trying to minimize this function. So we're trying to get into mean L. We're trying to go to minimize L. So what happens is, let's say if this is negative, right? So if this function is negative, what happens is if this is negative, and then this is a negative, if this is negative, both are negative, you can make the functional value very, very big. Okay, so you can make the functional very, very big if both are negative. So if mu is less than gx is less than 0, then L will, so L will sort of, then these two multiply together will be positive, then L is big. L will be bigger. The Lagrangian will be bigger. So you're trying to minimize because we always write g of x to be less than or equal to 0. This forces mu to be positive. It basically picks the sign to be positive. So here, mu is positive. So in the other case, so if we have h of x is greater than 0, then mu will be negative. Okay, so there's a sign convention here. So really, sort of, we will always pick this sign convention. So mu will always be positive, simply a convention you pick. Okay. And the reason that lambda for equality constraints you don't have a sign convention is for equality constraints they're sort of both bigger, right? So they have both bigger or equal to 0 and less than or equal to 0. So there's no sign convention for that. But here we will have a sign convention. Okay. So with this convention, the way you solve the problem is basically you just go try every possible, you guess a possible combination, try it, see if you get the problem is feasible, you get mu to be positive, and you get sort of lambda, you get the same lambda for all the equality constraints. If that's the case, you're done. If that's not the case, try again. That's a solution procedure. So before going to that, let's take a break. Then we'll go through a bunch of examples of how this trial works. Okay, so let's take a 5-minute break. Right, so what could happen for this problem is that you can guess, right? So you can ask, what happens if I guess this way, mu turns out to be negative? Right? What, could that happen? Turns out no. You're guaranteed one of these choices will be correct. So in this case, there are only two choices. So the first one is wrong, the second one is correct. It's not possible for this mu to turn out to be negative, even though it's very hard to tell in this equation. It's very hard to tell in this equation. So again, to show that, sort of way beyond the scope of this class. Really, that requires a lot more, essentially geometry than we're going to do in this class. But you can always assume one of the guesses will be correct. So when you're doing your homework, if it turns out you say, oh, I could not find a feasible solution, all of them are wrong, then you have made a mistake somewhere. There is a one and only one correct guess. There will never be two that's both correct. There'll never be a case when none of them are right. There's exactly one right guess, okay? And the problem in the homework is set up in a way that you should get there with relatively few trials. You should get there with fairly quickly. That's not to make you do a lot of trials, right? But now in your final, since final will be take home, you'll see a larger version of this. Right? So you have some time, you should just try it. Okay. Question with this example? Let's see. This example, right? So when you write your solution, you should document this, right? So you should document this process. Don't write a solution saying you magically guess all the inequality constraint in the first go and then solution you get, right? So you should document how you went about this process. Okay, so especially when you have like A constraints, the chance of you guessing exactly which one is right is quite low, right? So you should document some process you went through this. Okay, so we're now going to look at the graphical solution. It doesn't really add anything. For economic dispatch, what we have is you have mean. Okay, so to dispatch there always you can write the form as x1 minus x2 equal to 0. And then here you have g1. G2. G3. G4. And so this growth is actually quite fast on you. This will grow fairly fast on you, but but again, but the procedure is the same. Procedure sort of is exactly the same as before. The thing again to remember is remember this less than equal to sign. Okay, so the most common mistake in this class is you write x1 minus 1 x max less than equal to 0. Then again, you write x1 minus x mean is less equal to 0. That's the most common type of mistake, is you got the sign wrong. And that will give you some very weird solutions. So if you get solutions that doesn't make sense, check this signs down correctly. Okay, it must be something less equal to 0. That's sort of the requirement for this type of problems. Right? So we're going to say the mu is 0. And what you can do is your conditions, this kind of conditions, what you have is you have, sorry, condition will be the okay, so let's do this with both our lower and upper bound. Let's just write this thing out. Okay, so now you have both upper and lower bound. So you basically have 4 things. Thanks off here. You just have 4. You have mu1, x1 minus x1 max, mu2, x1 mean, mu3, x2 minus x2 max, mu4, x2 mean minus x2. Okay, so just have sort of more of them, right? Then your optimatic condition is the same as before, it's just with more equations. So your conditions will be for the 0, right? So here you have, I'm going to take a partial derivative with respect to x1, so both mu1 and minus mu2 coming out. So this is the equation you get, okay? Have both terms, right? So x1 appears in 2 inequality constraints. So you have 2 of this mu terms coming out. x2 you have the equality constraint. Then we have, so you check. So you have all the inequality constraints. And mu1, x1 minus x. Okay, so this is basically this all this. So you repeat this for mu2, mu3, mu4. That's all the set of inequality constraints. All right, and here is basically then the solution is you go guess. Okay, so the solution procedure is you have all this, and you try to guess which one of these things is tight. And for each scenario, you go and solve and check whether it's constrained, whether its conditions are held. Potentially. Potentially. Right. So okay. So for this, right? So what is a good way of going about guessing? Given the fact that you know most of these constraints will not be tight, what is the right way to start guessing? What is the first guess you should make? Solve the unconstrained part. There's a way to guess, right? So really, your hope is most of these are not tight. So I will not engineer a problem where everything is tight. That's not nice. And so the problem is not everything will be tight. So the solution is one you solve. So guess no constraints are tight. Okay, so nothing is binding. You just solve the problem as normal and say nothing is binding. What you get is you get x1, x2. Okay, so you check. If these two solutions happen to satisfy all the inequality constraints, then you're done. If they satisfy one constraint. If not, then how should you guess next? Right. So next you look at which constraints are violated by your solution, right? Then you guess those are the tight constraints. Okay, so you look at these, you say, okay, if some constraints are not satisfied, which are the ones that are not satisfied? Make these the tight constraints, right? So two, if some constraints are not satisfied, guess that they are active or they are binding. Okay, so guess that. Right? So if, for example, if x2 turns out to be too large, then guess x2 equal to x2 max. If x1 turns out too small, guess x1 equal to x1 mean. Okay, right? So just try this kind of guesses. And then three, repeat the procedure. Okay, so you guess, then you check, then you guess, and you check. You keep repeating this. This sort of, you'll get a good solution within 3-4 tries. It doesn't take that many tries to get there. And so normally you don't see the case where the thing sort of jumps around. So you will see this, and the questions are constructed in such a way that this thing will, your guesses will converge in like 2-3 steps. If you follow this procedure, your guesses will converge. It will not be constructed in such a way that you have to sort of do combinatorial guesses. Okay, yeah, good. No, your computer is not doing this. Your computer is not doing this. So I'll say a little bit about interpretation, then I'll give you a high level of what your computer, how your computer does. I'll give you a high level of what your computer actually do. Okay. So before that, so similarly as if we give a interpretation of the equality constraint, here we'll give an interpretation of the inequality constraint. Okay, so interpretation of the inequality constraint is the following. It says, let's say you're minimizing this. Right, so let's say L minus X equal to 0 and X less than equal to K. Okay. Let's say this is your problem. Then what you can again think of this is, you can think of this as a function of L and K. Okay, so this is what you think about this as a function. Here, X is internal to the optimization problem, right? So X does not exist outside the optimization problem. It's like you're writing a program, X is within a function, right? It doesn't have no existence outside this function. So we think about this as, you think about this as this thing, right? So I have some f of L and K. Now you want to take partial derivatives of both L and K. You want to take partial derivatives of L and K. So how do you take this? Well, you write this out, dx plus lambda L minus X minus K. Okay, so this is how you derive this. So now you take partial derivatives. Your first partial derivative is what I saw before, right? So if you take derivative with respect to L, well, you know, you get the marginal price back. The second partial derivative is a bit more interpret this, right? How do I interpret this? So if mu is 0, means your constraint is not binding. So the derivative with respect to K is 0. It means if I change K a little bit, the problem doesn't care the fact you change K. Okay, so if this mu is 0, K, this F does not locally depend on the value of K, right? So if mu is 0, so this says then sort of at least locally there's no dependence on K. If you change K, it doesn't care. Now, what if mu is positive? What does this say? If you make K larger, what happens to your cost? Goes down, right? Which makes sense, right? I make the problem easier to solve if I make k larger, right? So if I increase k, x can range over a larger space. Then of course the cost has to go down, right? You have more choices for x. Okay, so here it says that cost goes down if k increases. That's why this is another argument for mu has to be positive, right? So if I increase k, I'm minimizing this problem. If I increase k, my minimum has to go down. Your minimum value has to go down. Okay, you're searching over a larger space in here. Okay, so that's why mu has to be positive. Mu cannot be negative here. Okay, so it's either k doesn't matter, which mu is 0, or k actually matters. Then if you increase the range for x, you get a lower objective function. Right? You get a lower value you can apply. Okay, so that's why mu is positive. So this is closer to how you would prove mu is positive. And you can do this kind of argument. Right? Any questions for this interpretation? Okay, so I won't do the example with economic dispatch. So Friday afternoon, that thing will take us 30 minutes. That's probably not the best thing to do. So here, let's think about how a computer will solve this kind of problem. So if you're doing this, how will you solve this kind of problem? Let's say. So this happened, right? So does anybody know who Danzig is? Ever heard of the word Danzig? Okay, so Danzig was a graduate student at Berkeley in the 1950s. And basically, at that time, they were looking at this type of problem. Then the professor basically wrote on the board saying, oh, I don't have a procedure to solve this. Danzig thought that was a homework question, went home, took a month and said, oh, I'm sorry, I solved your homework question. I'm late for this homework question. Turned out to be very challenging, but then I solved it. And basically, he solved this open problem because thinking it was a homework question. Okay, so now let's try this. Let's think of this as homework question. How will you design a computer to solve this? Time was, this kind of argument was known for a very long time. You look at these multipliers, but seemingly you have a combinatorial problem of trying the multipliers. Okay, so what Danzig did was sort of the first algorithm people came up with is there is an intelligent way of trying. So here we're going to do trial and error. You basically can eyeball it. What he come up with sort of, the related problem called a simplest algorithm. It tells you which way you should try to look at for this, which of this Lagrangian multiplier turns out to be non-zero. So that's the so-called simplex algorithm. That was used even today in computer how to solve this. Basically, it's still trial and error, but it's a procedure that tends to work very well in practice. There's sort of way you should try which of the constraints are tight. That's sort of the simplex algorithm. But turns out that algorithm, at worst case, it still has has exponential complexity. So you can engineer very weird looking problems where you have to try all the combinatorial problems. You have to try them all. You have to try basically all of these. Okay. So for a long time, it was not known for this type of problems whether there is a polynomial time solution, whether we can have a Git polynomial, whether we can have sort of fast solution. Then after a while, people sort of figure out, how do you approach this? How do you get a polynomial time solution? So the idea is the following. So the way we solve this in the computer is you do so-called a interior point algorithm. And this comes from the fact that, again, that solving unconstrained problem is easy. Solving constrained problem is very hard. Okay, so the idea is the following. If the problem is unconstrained, I know how to solve it. If the problem is constrained, I don't know how to solve it. Right? So the question is, can you turn this into an unconstrained problem? Is there a way I can turn this into unconstrained problem? Can you think of a way to somehow move this thing upstairs? It's close to Lagrangian, but you need to do something else. Because what the Lagrangian says is, right, so you have the Lagrangian as plus mu g of x, but the Lagrangian still have constraints. Namely, this thing has to be greater than 0. This has to equal to 0. So how do you eliminate both of these? Right? The Lagrangian says this has to be greater than 0, g of x has to be less than 0. Lagrangian doesn't eliminate constraints. Lagrangian helps you to derive conditions. But the conditions are only useful if you know where to check, right? So I don't want those sort of conditions. I just want to, let's say I just want to do gradient descent on this. Is there a way to do gradient descent? Is there a way to turn this constraint? Is there a way to move it upstairs? Very close, very close. What you want to say is, I want something that has a following feature. Okay, so I want the following feature. I want to turn this into minimizing f of x plus h of x, where this h of x has a following feature. H of x is 0 if g of x is less than or equal to 0. H of x is infinity if g of x is greater than 0. So if I can find you this function, solving this problem is equivalent to solving that problem. It says if you're not well satisfying the constraint, I'll give you infinite penalty. I'll give you infinite penalty. If you're satisfying this constraint, I don't care. The constraint there. So this is the question, so what does this function look like? The function looks like this thing, right? So it's 0 here, then sort of infinity everywhere else, okay? Of course, this is not a very nice function. So is there a nicer version of this function? Can you think of a function that's sort of almost like this? Not a second one, not a second. What function goes to infinity when something approaches there? So what function, right? So what function is, if you're far away from 0, it doesn't care. But you're very close to 0, it shoots out infinity. Not quite, not. I don't want to be a constraint, right? Power 2 discuss. What is the function? What function? Right, so the function we should use is a log. What you want to use is you want to use a log function. So you look at this function is look at log of minus g of x. Okay. So you want to look at this log function. So what does this log function look like? This log function looks like if gx is right. So I'll look at the minus log actually. Okay. So you look at minus log of g of x. When this is close to 0, log of 0 is minus infinity. The minus log of 0 is infinity. Okay. But this function grows very, very slowly if g of x is very big. Whereas this function grows extremely slowly when g of x is big. Because log of something is essentially constant. That's what you think about it, okay? So this function satisfies the condition that if this bound is satisfied, right, if g of x is less than 0, minus gs is positive, log of large positive numbers is very small. Right? Log of 0 goes to infinity. So this is called a log barrier function. So the word barrier comes from the fact that this is a barrier. You can't go through this. Okay? So what you solve is you solve the following problem. You solve fx. Now you put a sort of constant up to here. Well, the way you do a constant, you put alpha minus log minus g of x. Okay, and you take, or what this is normally written as, yeah, alpha works. Alpha from large number to 0. Okay, so what you do is you pick an alpha. right? For alpha that's not 0, this constraint is enforced exactly. You cannot, g of x cannot be positive, okay? Then what you do is you find a solution, then you reduce this weight factor. When this weight factor gets close, smaller and smaller, still you cannot, g of x cannot be positive, right? Because log of 0 is infinity. So however small this alpha is, infinity will win. Okay, so what you do is start with some alpha, then you keep reducing this number. When alpha is sufficiently small, you basically get to the original problem. You get to the original problem. This is called the interior point, is because you start with some possible, right? You start with a feasible solution. It may not be optimal, but at least feasible. Then we'll give you a sequence of unconstrained problems you can solve. This is a sequence of unconstrained problems. And this sequence will converge to x star. This converges to x star. And the way this works is there is a way to decrease alpha in step sizes, whereas convergence happens in polynomial time. That's basically the idea. You don't have to, right? So how to take alpha to 0? There is a procedure of taking alpha to 0, which will converge in sort of polynomial time of steps. And this gives you a polynomial time solution of the problem. Okay. So this is how your computer will go solve this fast problem. The computer basically builds this and then solve the problem by solving a bunch of unconstrained problems. So computers are very good at solving unconstrained problems. The way a computer handles constraints is through this barrier function. Okay. This was a huge achievement in the I guess late 80s, early 90s, as people actually figured out a polynomial time solution to this kind of problem. This is right. So for example, there's sort of awards named after the guy who discovered this. This is due to Numerovsky at Georgia Tech, who showed this is okay. The proof is actually quite intricate. The proof requires bounding for how fast this can change and so on. But the basic idea is replace constraint problem with unconstrained problem. Then get your computer solved. And almost all the problems we have today is solving this type. So this, of course, is not doable by hand, right? We are not very good at solving this. So we're going to try and error. But you don't have to do try and error. This is how most solvers approach problems. Okay. Any questions for this? So there's a reason why this has a log. Right? There's other functions that does this, but log has a special property. So that property is sort of the fancy name that's called as this is a self-concordant function. Basically, what that means is this function sort of goes up fast enough when you approach the constraint, dies down fast enough when you're away from the constraint. And log is really sort of the right type of function you need for this, right? So log has special properties here. But this called a log barrier, and this type of thing works. Okay, so this is how things are solved in modern computers. Okay, so there's so designing this type of algorithm is its own huge field. We're not going to touch. We're going to touch this. Okay, and right. So one thing to take away is this is polynomial time, but still, when you have a lot of variables, can be slow. So that's why next class we'll see sort of some tricks that sort of the power system operator uses. Right. So this still cannot be super big, but at least here it works. This kind of thing works. And the field of right. So the entire field of optimization, convex optimization, relies on this type of technique. Relies on how to do this kind of thing. Okay. So let's end the class here today. Next class we'll walk through sort of trial and error for a much larger economic dispatch problem. If you get very bored in that problem, then I encourage you to take sort of more advanced classes. So you don't have to do that by hand. Okay. But the next class we'll do one by hand. Right. Okay, thanks guys.